Hey everybody. We're going to go over the chain rule today, which is a really powerful rule for taking derivatives. With the chain rule, you can it pretty much unlocks all the other, any kind of function you'd need to take a derivative of, because the chain rule is used for when you have a composition of two functions, and really two or more functions. Two or more functions, yeah. So let me just lay it out for you. The theorem says that if two functions f and g are both differentiable functions, and capital F is f composed with g, in other words, f of x is f of g of x, then capital F is also differentiable, and its derivative, f prime of x, is f prime of g of x times g prime of x. In alternative notation, if you let y equals f of u and u be g of x, dy over dx, which is the derivative of y with respect to x, is dy du times du dx. And you can see this actually, when you write out these differentials like this, you can kind of see what's happening where the du's cancel, so to speak. And that's the chain rule. So let's take a few examples and just see how we work with the chain rule in practice. All right, let's take f of x as the square root of x squared plus 1. So if we were to kind of write this in terms of f's and g's, we would say like the function f of u, I write it as the square root of u, and g of x would be this inner function x squared plus 1. So f prime of u, well, that's going to be, as we've done before, 1 over the square root of u. Oops, there's a 2 in front. We've done this a few times so that I'm just jumping straight to the derivative. G prime of x is 2x. Now, if I was to write this out, we're going to get f prime of x is going to be 1 over 2 square root of, not u, I'm going to replace u with this here. This is like my u, x squared plus 1 times 2x. So I probably would cancel the 2's and write this as x over square root x squared plus 1. That's the way that I'll probably write this. Okay, so here my functions are, I have the sign of u, and I'll write u is equal to x squared. So the derivatives are going to be the cosine of u for the derivative of the sine, and it'll be 2x for the derivative of x squared. So when I say y prime with respect to x, right, it's going to be the cosine of not u, but x squared times 2x, which probably you would write 2x times the cosine of x squared. I want to contrast that with, y equals sine squared of x, which, if you recall, sine squared, this is just another way of saying this is the sine of x squared. Here, my first function is going to be u squared. That's my main function, and my kind of inner function, u, is the sine of x. So then I'll have 2u for the derivative of u squared, and then I'll have cosine x for the derivative of the sine of x. So y prime in this case, I should really divide these because these are two separate examples. I'm redefining y. It'll be 2 times u, which is the sine of x, times derivative of that, which is like u prime, it's cosine of x. 2 sine x cos x. I'll leave it at that. So the chain rule has this kind of property. You treat this variable, this like expression, whatever is inside here, as like an unchanging object first, while you take the first derivative of like the main outer function, and then you take a look at that, and you kind of dig in. Now, In fact, the chain rule, if you have many layers, you can actually do this with multiple layers. We'll see some examples of that a little bit later. Let's look at if we combine the chain rule with the power rule, we can sort of generalize a certain situation which is going to come up often. So if n is some real number and u is g of x, if we take the derivative, if we want to take the derivative of, so if n is a real number and u equals g of x, so u is a function of x, the derivative with respect to x of u to the power n will be nu to the n minus 1. So that's the power rule part. We multiply this by du over dx. So that's the chain rule part. Or you could write it without the u involved. You could write d over dx. The derivative of g of x to the nth power is n times g of x to the n minus 1 times g prime of x. Okay, so as an example, if we have y equals x to the third minus 1 to the 100th power, the derivative is just going to be 100 times x to the third minus 1 to the 99th power, but we don't stop there because the chain rule says now we look at this function that's on the inside. The derivative of that is just multiplied on the end. It'll be 3x squared. Minus 1 is gone because that's constant. Yeah, so we probably would clean this up a tad. 300 x squared times x to the third minus 1 to the 99th power, and I'm not going to do anything else with that except clean up that 0. All right, let's take a look at this. F of x equals 1 over cubed root of x squared plus x plus 1, which actually, to do this, I'm going to rewrite this as x squared plus x plus 1 to the negative 1/3 power. Writing it like that makes it a lot more clear that this is a power rule problem with a chain rule component, right? So f of x, f prime of x will be negative 1/3 times this inner function unchanged, x squared plus x plus 1, and that's going to be the negative 4/3 power, because negative 1/3 minus 3/3, that's negative 4/3. Okay, so that's my exponent. Then we multiply it by the derivative of x squared plus x plus 1, which is 2x plus 1. Just using the power rule on each of these components one by one. So in fact, we'd probably want to write this as negative. Down below, I'm going to have, let's see, I'll just write this as the negative 3 times it's a cubed root of x squared plus x plus 1, and this, I want to have this to the 4th, which I can put either place. I'll put it in here, and then up top we'll have 2x plus 1. That's one way to write this thing, although it's messy no matter which way you write it, really. Okay, let's see how this quotient rule gets into the mix. So we're going to have this t minus 2 over 2t plus 1 to the 9th power. So the first derivative, we're going to, it's going to be 9 times t minus 2 over 2t plus 1 to the 8th power. Now I have to multiply by this derivative, the derivative of this fraction, or this rational function, which I'm going to use the quotient rule. Remember, the denominator is just the denominator squared, so I'm going to start with that. And then it's going to be the derivative of the numerator, which is going to be 1 times the denominator, 2t plus 1, minus the numerator, t minus 2, times the derivative of the denominator, which is a 2. And I'm actually happy with that just as it is. I don't want to spend a lot of time cleaning it up because it's going to be ugly no matter what. So I'll just leave it like that. I mean, this in here could tidy up a bit. Should I? Actually, now that I look at it, I think that we're going to get rid of some t's. Let's see what that would, what is that numerator going to be? We're going to have 2t plus 1 minus 2t, and then minus a minus, it's going to be plus 4. So that's what we have up there, the 2t, that's going to be a 5. Yeah, I kind of like that. 5 times 9 is 45. And then we have t minus 2 to the 8th. over 2t plus 1, that's to the 8th and also squared, so that's all together to the 10th power. Yeah, that's nicer looking. All right, so I take it back. I am going to clean it up a bit, but that's purely for my own my own preference. Okay, so now you can see we're growing this function. What we have here is the product of these two powers. So what you need to look at is kind of what is the framework of this thing. What we have is y is like, it's like f times g. F is, we can write it like u to the 5th, and g is, I'll call it v to the 4th. And then u is the 2x plus 1, and the v is the x to the 3rd minus x plus 1. So altogether, we have to like kind of structure this as, okay, outside of everything, we've got to use the product rule. Then we're going to have the, then we have to apply the chain rules. So y prime, it's going to be, I'm going to write it out in the abbreviation f prime g plus f g prime. Now, what is f prime? F prime, it's going to be 5u to the 4th times u prime, which is to say the derivative, I didn't write that 1 there. It's the derivative of 2x plus 1. So it's actually 5 times 2x plus 1 to the 4th times 2. And g prime is going to be 4v to the 3rd times v prime, and that's v prime is the derivative of that x to the 3rd minus x plus 1. So that's going to be 4. I don't have a lot of room to write it there. I'm going to write it down here. G prime is going to be 4 x to the 3rd minus x plus 1 to the 3rd times 3x squared minus 1. Okay, so this is everything I need to put into my derivative. So f prime, which is this, I'm actually going to write this as a 10 times 2x plus 1 to the 4th times g, which is this whole thing is g, this whole thing is f, right? So times g, which is x to the 3rd minus x plus 1 to the 4th, plus f, which is 2x plus 1 to the 5th, times g prime, which is 4 x to the 3rd minus x plus 1 to the 3rd times 3x minus 1, 3x squared. Clean this up a tiny bit. Just make it totally clear that this is my answer. All right, I'm going to put this down below just to have it kind of a little bit more neat. So you could see it's all very mechanical. I mean, you can do it step by step by step. It can become, these derivatives can become kind of messy, but you can do them. And at this point, I would not expect you or want you to spend your time trying to expand things out and all of that. Not necessary. Okay, check it out. So check it out. This function, s sine of cosine of tangent of x. So we have 3 layers, so we're going to apply the chain rule. Well, 3 layers. I guess will we say to apply the chain rule twice, because you don't apply it on the innermost layer. Anyway, so f prime of x. I'm going to illustrate it with primes in order to kind of show you what it's going to be. So it's going to be the sine. So we first off, it's the cosine. That's the derivative of sine. Cosine of cosine tan x times cosine tan x prime. Now, I'm going to kind of bring this down. We have cosine of the tangent of x that hasn't changed. Multiply that by, what's the derivative of a cosine? It's the negative sine of the tangent of x. But we have to multiply this now by the tangent of x derivative. Okay, so we bring this down and we bring that down. So it's the cosine of the tangent of x times the negative sine of the tangent of x. And what's the derivative of tangent? Remember that? It's the secant squared of x. So that's this whole thing. So you can see applying the chain rule twice and kind of how this flows. Chain rules, it's kind of nice. You have to remember it's all multiplied. You multiply the derivative of that inner function. And if that derivative of the inner function requires a chain rule, then you apply the chain rule, and then you have a product of three things, right? So this is this times that times that. Here's another multi-layered example. Y equals the square root of the secant of x to the third. So the first layer is the square root function. And remember, the derivative of that is 1 over 2 times the square root of that thing that was inside it, which is a secant of x to the third. I'm going to multiply this by the derivative of secant of x to the third. Do you remember the derivative of the secant? The derivative of secant of something is the secant of that thing times the tangent of that thing. But we don't stop there because we have to multiply it by the derivative of x to the third. And that, as you know, actually before I move on, I want to just, since I have secant to the third, or secant of x to the third on the numerator, and I have square root of it on the denominator. So I can put a square root of secant to the third. So I'll put the square root of the secant of x to the third here. And I'll write the tangent of x to the third. Down below I have a 2. But what's the derivative of x to the third? That's 2x squared. That's 2x squared. And in fact, the 2's even cancel. So I can write x squared. I'll put the tangent of x to the third out front, because then it's clearly not underneath the square root. There we go. There's our derivative. Okay, so we've applied we've learned the chain rule, gotten some practice, and of course you need some more practice. So get some practice. All right, bye.